can't be a scientist without being a bit childish. Hello and thanks for watching the video. Today I've got a friend, well my sister, but she is a friend, asking some questions about radiation and the fear of radiation, that sort of thing. So I'm going to do some basic questions because there's some videos to come about radioactivity, going into detail a little bit more about different types of radiation and all that kind of thing. So this video is going to address a few things broadly. So,
but first of all, actually, before I get into these questions, just briefly tell me what radiation is.
Well, the term radiation is often misunderstood. People use radiation to describe the fear of things like Fukushima. So there's radiation coming. But radiation actually just means energy emitted from a source. So that could be like me. I'm emitting infrared heat, which everybody is, and a light bulb is radiating light. So that's radiation. It's electromagnetic radiation. So the term radiation is a broad thing, and people often don't realise that. But the type of radiation they're inadvertently talking about is ionising radiation. That's the type of radiation that can actually do damage to cells and atoms. Ionising radiation basically means radiation with enough energy to rip electrons from atoms, to ionise them, and to almost blow DNA strands to pieces and things like that. That's the type of radiation that people are really fearing without realising.
Okay, so why are people so scared of radiation?
I think there's a lot of reasons why. I think a big one is actually the media, because whenever the media covers something like Fukushima, they always approach that small case scenario where what's the worst that could happen, and then that's all they'll talk about. They'll interview a scientist, but they may well edit out the bit about chances of this happening as next to nothing. But it also goes back to school as well. Although we are taught about radiation in school, I remember being taught a little bit about radiation, but I left school not knowing a great deal about it, and there's no way I could have told you whether, if I saw something on TV, if that were dangerous or not, because from school you don't learn these things. So maybe that should be something that's covered, just to stem that fear a little bit, because a lot of the time people are fearing something that's much less dangerous than a lot of other things that's going on in their immediate vicinity. They just don't realise.
Talking about things in your vicinity, do mobile phones and microwaves give off radiation like nuclear reactors do?
Huge misconception again. I know some pretty smart people as well who I've walked up to with one of these. I might have been visiting the house, something. I've taken these sort of toys with me because I'm a geek, and they'll say, "Oh, try it on the telly, or try it on my laptop or mobile phone." And I said, what will it read? And I said, nothing, because it's a different type of radiation. This goes back to that radiation as a broad thing. People assume that they give off radiation that's damaging, but it's not. The radiation that mobile phones and laptops and microwaves give off is microwave radiation. So it's on the electromagnetic spectrum. It's a form of light that we can't see with the naked eye, but it's not got the energy to rip electrons off atoms. So it's in my eyes, it's not dangerous at all. There's a lot of hype about microwave radiation, but the science so far says that they're perfectly safe. So no, they don't emit that.
So how much radiation is dangerous?
That's a huge subject in itself, mainly because of the current model in which we talk about radiation, something called hormesis, which basically says that any radiation is bad, or all radiation is bad. So we base everything medical and everything, and nuclear workers and everything, all that is based on this hormesis, which in modern science, and certainly in some of the research work that I did at university, is pointing to a different model which is much more likely to be accurate, which is called the linear no threshold hypothesis, which basically, if you see it on a graph, it shows that a certain amount of radiation up to a certain point is virtually harmless, and in some cases can even be beneficial, which I'll talk about in a second, and then it gets dangerous, whereas the current model, hormesis, just shows us a point at the bottom of the chart where you've got a slight chance of getting cancer, a bit more here, a bit more here. And although it's true to say that there is a finite chance that an ionisation event can give cancer, it's an extremely small chance. What usually happens in this research, you can Google this up, if you type in linear no threshold hypothesis, you'll find a lot of data that supports the fact that heightened levels of background radiation can sometimes be beneficial. This has got a lot to do with the fact that your body has a repair mechanism. There's radiation all around us, which is crucial for people to understand. There's ionising radiation coming from everywhere. It comes from above you, below you, in the rocks. You breathe it in. It's in your bones. It's in your body. It's even in the person you sleep next to and the food you eat. So understanding that it's there to start with, that your body has a repair mechanism for that, so it can repair damaged DNA strands and cells and things like that. And evidence shows that if you are exposed to slightly higher background radiation levels, it kicks that repair mechanism in a little bit more. Almost like you could even think of it as being like your immune system. You know, you need to be exposed to something to become immune to it, and sometimes being exposed to a little bit more than usual makes you more immune to it. If you understand that.
Makes sense.
Radiation seems to work that way. So that hypothesis needs to be, I think, in the future made standard. So that gets back to the question you asked about how much is dangerous. If you just look roughly, if you receive a dose of 2 sieverts or more, the chance of actually dying from that is very high. If you receive 4 sieverts over a small amount of time, that's almost certainly going to be fatal. Something like 99% chance of you dying from 4 sieverts. But that's a huge amount of radiation. We don't even measure that in thousandths of a sievert. We measure it in millionths of a sievert for day-to-day life, microsieverts per hour, which is what a lot of these Geiger counters read. They read in milliroentgens per hour or microsieverts per hour.
So a microsievert is 1 millionth?
Is 1 millionth, yeah. You're not going to come across things like that on a day-to-day basis, but the background radiation, for example, is something like 0.2 microsieverts per hour. It's not even 1 microsievert, below that 1 millionth. And to be exposed to something like 2 sieverts, you need to be stood near a nuclear disaster like Chernobyl. Some of the people that died at Chernobyl were exposed to 2, 4, and even higher. Some people were exposed to 2 sieverts and lived with no side effects whatsoever that they could see.
So everybody deals with it differently.
Yes, absolutely. Yeah, that's one. It's a bit. It's difficult to get an analogy, but in the same way that people that drink alcohol, some people there's no standard that says
there's no
4
rule,
pints will make you drunk, because everybody's different. Radiation is exactly the same, so you don't know. If you go to the doctors and you get transferred for an X-ray or a scan, you're likely to receive more radiation in them scans than you would anywhere else in the world from natural things. For example, a mammogram to prevent breast cancer, or to prevent breast cancer. You receive a dose of about 3 millisieverts all in a short period of time, an acute dose. That's about 2 years worth of background radiation in the UK. In the UK it's about 1.5 millisieverts per year background radiation. So in that small amount of time you get that huge dose. But the statistical chance that might give you cancer is far outweighed by the fact that if you've already got it, it's better to see it on the X-ray, the scans. So it's such a small chance that they would cause
How
any
much
problem.
radiation is given off by a nuclear bomb?
Different types, a huge subject again. There's different bombs that are designed to give off more radiation than... The bomb is designed for the maximum amount of destruction. So the amount of radiation it gives off is just a byproduct of it. But so like the bombs they dropped on Hiroshima and Nagasaki, 15 kiloton in Fat Man, which was the first bomb that was dropped. And in the second bomb, it were Little Boy and Fat, I can't remember which way around it was, but it were a 20 kiloton bomb. And the radiation levels that are around there today are only 2 or 3 times higher than we find in the UK in the background. So it didn't, long term, it hasn't caused that much radiation, but at the immediate vicinity when it happened, there was a hell of a lot. A lot of the deaths, people that survived it died after from radiation. But there is dirty bombs where they designed neutron bombs, for example, where when they blow up, the explosive power is swapped in favour of releasing neutrons, which when they hit people, it's heavily ionising radiation, and the dose is usually acute. They're nasty bombs. I mean, they're just designed to kill people in not such a nice way. But actually, again, that's another. Maybe I'll do a subject on nuclear bombs, and definitely on nuclear reactors.
My last question is all ionising radiation bad?
No, not really, because we use it in so many good ways. Like I said, medical for one of them. Without X-rays, we won't be able to see broken bones and things like that, and different types of scans, like I said, the mammogram scans or even dental X-rays. So even though you're being given an acute dose of radiation that's much higher than you'd find in nature,
it's done for good.
Exactly. Would you rather walk around with a broken bone that could end up giving you serious infections inside, or get the, half a millisievert from an X-ray or something, with its finite chance of giving you a problem in the future, tiny chance, or do you die in a few weeks' time from serious bacterial infections and all that kind of thing? The benefits are outweighed. Again, the fear of radiation goes back to that again. These are quite large amounts of radiation. in relation to what we see on a day-to-day basis, but yet don't cause too much harm.
As always, that was very fascinating.
There's one more
Thank
thing
you.
I can mention as well,
Mm-hmm.
which I put on the video, and that is if people are worried about things that are radioactive. So if you find something in your house like this is our great granddad's World War One pocket watch. This is quite active. He had this for many years. It was in World War One as a sniper, and he was given this. I think it was standard army issue. This is really quite active, and I can demonstrate that if I put this Geiger counter on.
I still can't believe how.
You'll hear the odd click from this as it measures background radiation, but if I put it on the actual watch. Now, one thing you'll notice about this sounds bad, doesn't it? But if I put, say, 10 centimetres or something between it, that number drops to less than half. But if I double that distance, it drops by a factor of 4. And if I do that again, next to nothing. This is because this works a bit like car headlights. It's the inverse square law. So putting distance between you and the object means you receive less radiation from it. It's not like having it right up against your face. You might recall if you see a headlight close up, it's dazzling, isn't it? But if you see it from about half a mile away,
not as bad.
You can't hardly see it. And that is because it's a point source where the energy is coming from, and it spreads out in all directions. You can imagine if you get a balloon that's not blown up and you put lots of little dots on it, they're very close together, and you start blowing up the balloon, so the outside, the circle, the area of it expands, and the dots move away from each other. So that means that as you get further and further away, there are less photons per unit volume getting to you. And the same with the radiation coming from this. The gamma photons that are coming from it is less and less in the same amount of space because they're having to fill up a bigger amount of space. That's the inverse square law. So you can put distance between you and an object. So it's perfectly safe to have this in the house. If you don't want to have this near you, just 6 foot away makes a dramatic difference. And also shielding anything you put in front of it. Usually something like aluminium and then followed by lead is good because that slows down the photons and stops them escaping as much. And also time. The less time you spend with something radioactive, the less dose you get. So, there's a big difference between 1 second of me doing that and then doing it for a full hour.
Yeah.
There's a huge difference. So that's another thing to mention about radiation. But again, future videos on that.
Okay.
Is that something else? I hope that answered a few misconceptions and stuff anyway. But again, there's a lot of things in there that cover a broad variety of different things. So we'll go into different videos and go into the science a little bit more to answer some of them questions. And also there'll be some videos coming soon to do with telescope astronomy and some reviews. You might see the big boy behind me, which is going to do a video on that soon. Lots more radioactive videos and stuff to come. So I hope you enjoyed that, and thank you for watching. Really appreciate it. Give it a like. Trying to do a video on science and you've got this. Yeah?
Hey, you too!
That's what I'm working with. Today it's going to be a video. I'm not going to be asking questions. That's stupid.
It was going to be about the fears of radiation, but first of all, obviously. Oh, don't start laughing.